Okay, we've looked at pressure, now we're going to move on to wind. So, what is wind exactly? Wind is just air in motion. We'll just start with simple. When you're out there walking and you feel air in your face moving by you, that's the wind, the motion of the air. You can see it in the rustling of the leaves sometimes, or the tree branches moving. Sometimes it's very light, hardly even notice it, and other times it can almost blow you over. So what forces, and we've talked about a force with pressure, control the speed and direction of the wind. You're going to find out pressure is one of the biggest ones. So there are local motion of air measured relative to the Earth's surface is wind. So we already talked about mass, air pressure. So the typical forces that act to make wind are the air pressure gradients. So we'll talk more about those. Centripetal force, we will talk about what that is. The Coriolis effect, which I am sure is going to cause some interesting thoughts in your mind. And friction and gravity, all of which make wind. So pressure gradient force. Take a quick peek at a pressure map. Notice the low pressure here and the high pressure back here. There's a pressure gradient. It's not a lot. That is moving in that direction. This air wants to get over here to fill in this hole. Think of it as if you dug a hole in the ground and the dirt just keeps wanting to fall back in, or your sand at the beach. That's what air wants to do. It's trying to fill in that hole. So the air from high pressure is always rushing towards low pressure, and that means that the high pressure would diminish, supposedly. So that is the first force. The bigger the pressure gradient, the more that force is going to be. So the more lines you see on a weather map, tighter together, of isobars, the stronger the wind's going to be because of the pressure gradient. Today, there's not much wind. There's not a lot of air motion whatsoever out here. So that is pressure gradient force. It acts perpendicular to the isobars. What's the next one? Well, centripetal force. If you're in a car and you're driving around a curve, what keeps you from flying out off the curve and continuing to go in a straight line? It's something called centripetal force. It's the force pulling you in a circle. It's always inward acting towards the center of that curve. So when you're going around a corner, it's always acting inward towards so it keeps you going in that circle, that part of the curve. So that is centripetal force. You'll see it on a weather map because winds blow sometimes in curved paths. And that is what centripetal force is defined as. It's not necessarily anything complex, but it's something you can feel when you're driving a car or running around a corner and you try to pull you away from that corner. When you're trying to turn real quickly. Coriolis effect. The Earth rotates, and boy, this would be a whole lot easier if it didn't. But the Earth rotates. So, and the fact that the Earth rotates means it's going rotating faster and faster the closer to the equator you get. Because let's face it, the equator is a lot bigger around than the area around the North Pole or the South Pole. So the Earth has got to rotate a lot faster in those areas. So the Coriolis force is basically a measure of that rotation in a way. Think about it. If you start out here at one time, a little bit later, the Earth is going to have rotated some, and there's going to be a direction off to the right where the force is acting. Coriolis force in the northern hemisphere always acts to the right of the wind. It also acts on a billiard ball. You might not think about this, but if you're a really, really good pool player and you're playing a tournament up in Alaska, for example, Coriolis force is relatively strong up in Alaska, turning things to the right more. It actually has an impact on the motion your ball is going to travel. May not be a lot, but if you just hit the edge of the pocket instead of where you wanted to put that ball in, that can make a difference in getting in the pocket and not getting in the pocket. Now, if you moved way down here close to the equator, Coriolis force is very weak. So you might hit the same exact shot and have a slightly different location for the ball. So literally the best billiard players actually can sense this in where they're located at and how they hit a ball. And the longer something is in motion, the more the Coriolis force will act on it. So yeah, a ball is not in motion very long. But if you have winds that's moving across the United States, it may be taking 3 or 4 days, and that's 3 or 4 days where it's being pulled to the right, if it was moving out of the west. So Coriolis force will have more and more an impact, and it is the strongest by the poles, and the weakest, it actually goes to 0 around the equator. All things that are important in winds. Friction. Think about if you push a wind over top of a mountain. The mountain's going to slow it down. It's going to cause it to move around. Their eddy motions are called, and turbulence. All these things are winds and waves of slowing down air particles. If you go over an ocean, the ocean's pretty flat. The air is going to move quickly. If it comes back over land, the air is kind of rough. So it's going to slow down. So friction is stronger over land than over water. So if you're up near Lake Erie, the wind will blow more over the lake than it will over the land. So now we talk about gravity. Gravity, pull back towards Earth. It is what is always pulling the air down, and it has a huge impact on winds in the atmosphere. But it's always downward. So now that we've got all these forces, let's start putting them together. So in the meteorology, rather than put everything all together at once, we try to simplify it first because it can get very complex. So we're going to look at something called hydrostatic equilibrium, geostrophic wind, the gradient wind, and some surface and horizontal winds within the boundary layer of the atmosphere. So let's just take a look at the hydrostatic equilibrium. All right, we talk about the pressure gradient in the vertical, and I mentioned to you how strong it is compared to the horizontal pressure gradient, and it acts upward. The vertical pressure gradient is extreme. But, so why doesn't all the gas leave the Earth? Because it's in hydrostatic equilibrium. Gravity is pulling the gas back down towards the Earth so that it winds up being approximately, it reaches a balance. That balance is called hydrostatic equilibrium. Guess what? It's an approximation, so sometimes it doesn't work, like in thunderstorms. But other than that, overall, it's pretty good. So with that in mind, it means an air parcel should, if there's no pressure put on that air parcel, should never move in the vertical or in the up or down. But because pressure can be put, convergence may occur. Maybe it'll push the parcel upwards. Divergence may occur. Maybe it'll push it downwards. Maybe it'll hit a mountain range and get pushed up. All these things can move an air parcel. They don't necessarily accelerate it. They'll begin to push it in a direction. But there's no acceleration with that necessarily, upwards or downward. It just moves the parcel upwards because hydrostatic equilibrium says it can. So that is another key component of winds. It describes a way to look at vertical motion in winds, how the winds blow vertically. Geostrophic winds. Geostrophic winds are basically going to be straight. They don't have a lot of curve. So if you look at this, start at the air pressure. Remember, the pressure gradient always acts perpendicular, and Coriolis always acts to the right. You see it right here at the beginning. If you move that air parcel along that path that's been forced by that, you'll see the Coriolis is now more to the right. Pressure gradient is more that way. Eventually, they come into equilibrium. The Coriolis force and the pressure gradient force are balanced. The air is moving in a straight line. There's no forces acting on it other than these two. So you see this a lot in upper air charts. So let's take a look at one real fast, and let's go up here a minute. I can get you a better one than this. We're going to look at this. Let's look at 500 millibars today, which is about halfway through the atmosphere. Notice these winds out here. Here's your pressure lines. A little bit of a pressure gradient out here. They're blowing parallel to them, not across them, parallel. That's because they're in geostrophic equilibrium. So this is an example of that geostrophic force. So if we continue on from this now, there's a gradient wind. Gradient winds are when things move in a circle or around a curve. So now we have the pressure gradient force, Coriolis force, and the centripetal force all working together. They're all combined to moving winds in a circle. You can see that again. We looked at surface weather maps. They tend to move in a circle around a high pressure. So these are gradient winds. They just have all three in it now instead of just two. Finally, when you add friction in, friction is just another force, and it just slows the wind. So it allows pressure gradient kind of to become a little more dominant. So that's why when you look at the surface, there's more friction. You'll see the winds kind of blow outward from high pressure. They're blowing in a circle, but they kind of blow away from it. Low pressure, they kind of blow inward towards the low. Even though they're going in a circle, still, they kind of have an inward tendency. We talked about divergence and convergence just a little bit. Think about it. If the wind's blowing outward, you're getting divergence. So air is tending to sink, to take its place here where this high is. So you have a vertical motion downward. If you have vertical motion upward around the high pressure, low pressure, then you wind up with air moving upwards. So this is just looking at the winds. All these combine to make your winds. And they can act in different levels in different ways. And here's the continuity of the winds. If you have horizontal convergence aloft, you might probably have sinking air, and you'll probably have horizontal divergence, like I was just showing you at the surface. The winds are going to always work together. If you have convergence at the surface, you probably have divergence aloft. And that's how you get the cyclones that we're going to talk about. Another thing to think about is over a lake, for example, when you feel the wind hitting the surface at the edge of the lake, the wind's going to slow down, and you see these clouds popping up there, maybe even a thunderstorm, or at least maybe a shower, maybe even a snow shower in the wintertime. That's because the winds have been moving faster over the lake, and they're getting slowed by the mountains, the rough terrain. And when that happens, they start going up. They got that convergence, and they be pushed upwards. So there's your continuity of winds again. We can look at winds. We monitor winds all different ways. One of the things I did want to mention with the anemometers that are used nowadays, the anemometers are all at 10 meters. What does that mean? The air that we're measuring, that you hear when you have a wind direction or a wind speed, is 33 feet up. So it's not at the surface. So you might get a little bit of different wind down there at where you are. So one other thing I wanted to show you with wind, just very quickly, is wind can be actually calculated by watching how clouds move. This is the derived wind on a satellite image over the United States. Notice how the yellow indicates winds of clouds that are roughly 10,000 feet or less. So these are kind of lower level winds. Notice they're moving out of the north, down across eastern Ohio and in here. Notice the red up here. The red is above 25,000 feet, maybe over 40,000 feet. Kind of a cirrus, kind of a jet stream kind of cloud. You can see they're out of the west. We talked earlier about winds moving in different directions. And you can really see that here. We have an easterly wind at low levels and a westerly wind at high levels. And one of the things I was going to show you quick on this, if I can get it back up here, is there is a tropical depression out there right now. And it's not a big one, but tropical depression number 5. And it shows right here, as it comes back, right down in here, where this mass of clouds is that tropical depression. Here is North Carolina, for example. So you can kind of get a picture of where it is right there. It would be down towards Puerto Rico and all of that. So it's out in the middle of the Atlantic. Not much to worry about, and it's just a depression right now. So hope you got something out of the winds now, too. Have a little bit better idea of things. So let me know if you have any questions.